Okay, good evening everyone. Trust you're all doing fine. So good evening everyone. Today we are going to be dealing with coordination chemistry. So without wasting much of our time, whenever you hear coordination chemistry, you can simply refer it to as chemistry of coordination compound. Now, what are coordination compounds? What you have to note is that in the definition of coordination compounds, there are three keywords. The first one is central atom. The second is ligands. And what is connecting these two together is coordinate covalent bond. So whenever you hear coordination compounds, they are the compounds that consist of central atom and ligand. Now, what are central atom? What are ligands? Ligands are actually atoms or molecules or ions that are joining to the central atom. They are joining to the central atom. So how are they joining to the central atom? Is through the coordinate covalent bonds. Do you get that? So once you know that a coordination compound consists of central atom and ligand, then the next thing you have to note is that the ligand is joining to the central atom by coordinate covalent bonds. So in a particular coordination compound, how are you going to identify your central atom and how are you going to identify your ligand? Note, your central atom are mostly transition metals. Your central atom are mostly transition metals. So what are the examples of the transition metals? That can be iron, it can be cobalt, it can be nickel, it can be titanium, it can be manganese, etc. So that is that. So that's the first thing you have to understand. The coordination compounds consist of central atom and ligand. The ligands are the atoms or molecules or ions that are joining to the central atom via or through a coordinate covalent bonds. And mostly, your central atom are mostly transition metals, which are what? Iron, cobalt, nickel, copper, zinc, tin, manganese, etc. Now, that is that. Before I move further, you also have to know something about the central atom and the ligands. You also have to know something about the central atom and the ligand. Firstly, the central atom the central atom can also be referred to as coordination center. While the ligands can be referred to as complexing agents. Now, another thing you have to note is that the central atom are Lewis acids because they are electron pair acceptor. While the ligands can be referred to as Lewis base because they are electron pair donor. So once you have understood these two terms in a coordination compound, once you have understood that the central atom and the ligand, the central atom also referred to as a coordination center, ligand also referred to as complexing agents. You have to know that the central atom is also called the Lewis acid because they are what? Electron pair acceptor. They accept the ligand. While the ligands are what? Lewis base because they are electron pair donor. They attached central atom. Now, once you've gotten that, then you have to know some of the examples of the coordination compounds. Now, let me show you some examples of coordination compounds. Some examples of coordination compounds. Number one, we can have K3 FeCN6. Number two, we can have CuCN4 3 minus. Number three, we can also have CONH3 ClCl2. These are some of the examples of the coordination compounds. Now, let me show you some features that you have to understand in a typical example of a coordination compound. Now guys, taking K3 Fe CN6 as an example. Taking K3 Fe CN6 as an example. The first thing you have to notice is that 95% of the coordination compounds always possess these square brackets. 95% of coordination compounds always possess what? These square brackets. So this simply means that whenever you see a square bracket in a particular compound, that compound is likely to be a coordination compound. Do you get that? Now, the next thing you have to notice is that any atom or ion or molecule that is found outside the square bracket, any atom or ion or molecule that is found outside the square bracket can be referred to as counter ion. So this simply means that this potassium that is found outside the square bracket is an example of counter ion. Counter ion. Okay, so after you've known the counter ion, then you have to know something that if you remember the definition of a coordination compound, it consists of two major things. The first thing is what? Is the central atom, while the second thing is the what? Is the ligand. So you have to note that the ligands and the central atom, they are the atoms or molecules that are usually found inside the square brackets. So the atoms or molecules that are usually found inside the square brackets are the what? Are the central atom and the ligand. So this simply means that whenever you see a coordination compound, if you want to identify the central atom or you want to identify the ligand, then you have to check the inside of the what? Square bracket. So inside the square bracket, how are you going to differentiate your central atom from the ligand? Well, what you have to notice is that your central atom is always a transition metal. And once you have been able to identify the transition metal inside inside the square bracket, any other atoms that are present inside that square bracket can be referred to as the word ligand. So this simply means that Fe that is here is an example of the word transition metal. So this simply means that the Fe here is the word central atom. Central atom. Now, once you have been able to identify your central atom as the metal ion that is present inside the square bracket, all other atoms or ions or molecules that is present inside that square bracket would be referred to as ligands. So this simply means that Cn is the ligands. Now, once you have been able to identify your central atom, your ligand, and the counter ion, then you have to know something. What is that? What you have to note is that there is also what we refer to as the coordination sphere. Coordination sphere. Note. Coordination sphere. Coordination sphere. Now, your coordination sphere simply means the central atom, the ligand. Everything that is present inside the square bracket together with that bracket, everything present inside the square bracket together with in that bracket can be referred to as the what? Coordination sphere. So everything present inside the square bracket together with the square bracket are simply referred to as a what? Coordination sphere. But any atom or molecule that is found outside the square bracket are simply referred to as the what? Counter ion. So this simply means that in these examples I put here, the Cu that is here is representing copper. Hence, the central atom here is copper. While the Cn that is here is representing the what? Ligand. Because once you have been able to identify your central atom, all other atoms that are present will simply represent the what? Ligand. So this simply means that Cn is the what? Ligand. And if you check this particular example, there is no atom that is written outside these square brackets. So this simply means that in this particular example, number 2, there is no counter ion. But if you check for number 3, you're going to see that the first atom here is CO. Now, whenever you see CO, C subscript O, it represents cobalt. And whenever you see C capital O, it represents carbon monoxide. So these two things must not be confused. So for cobalt, it will be capital C, small o, while for carbon monoxide, it will be what? Capital C, capital O. So note that very well. So this simply means that here, this CO represents the what? Cobalt, hence it is the what? Central atom. Do not forget that inside the square bracket, there are always two things present. The first one is the central atom, while the remaining things are the what? Ligand. So since CO represents the central atom, all other atoms that are present inside this square bracket would be referred to as a what? Ligand. So this simply means that the first ligand here is NH3, while the second ligand here is what? Cl. So any other atom that is not found outside the square bracket will be referred to as a what? Counter ion. Hope you got that. Okay, that's fine. Now the next thing we are going to move on to now is how to ionize a coordination compound. Now, note, whenever you want to ionize a coordination compound, note, a coordination compound can only be ionized into two parts. Coordination compound can be ionized into two. The first part is the ionizable part, which is referred to as a counter ion. Number 2 is the non-ionizable part, which is the coordination sphere. Now, you have to understand that a coordination compound can only be ionized into two parts. The first part is the ionizable part, which is referred to as a counter ion, while the other part is the what? Non-ionizable part, which is referred to as the what? Coordination sphere. Now let us look at a particular example. Let's say you want to ionize this coordination compound K3 Fe K3FeCN6. Now, if you want to ionize these particular coordination compounds, the first understanding you need is that a particular coordination compound can only be ionized into two. The first part is the counter-ion part, while the second part is the what? Coordination sphere. That coordination sphere is referred to as what? Non-ionizable part. So this simply means that if a particular compound do not have a counter-ion, that particular compound would not be able to be what? Ionized. So we cannot ionize a coordination compound that do not have a counter-ion. We can only ionize a coordination compound that has both counter-ion and the what? Coordination sphere. So this particular compound, it has a counter-ion and it also has a coordination sphere. Do not forget that the coordination sphere consists of the what? Square bracket together with everything inside it. So if you want to ionize this, the first thing you are going to do is that you will split this compound into two. The counter-ion is potassium, which is K. Write it out. K plus the entire coordination sphere. Okay, now we've written this. So once you've written this, the next thing you have to do is to assign the appropriate charge. Everybody, we all know that this K represents the what? Potassium, and potassium belongs to group 1 element, and whenever a group 1 element undergoes ionization, they will become what? Positively charged. So potassium is a group 1 element in which all group 1 elements undergoes ionization by the loss of an electron. And whenever a particular atom loses an electron, it will become positively charged. So this simply means that this potassium, it belongs to group 1 element, it will undergoes ionization by the loss of an electron, then it will becomes what? Positively charged. So potassium will carry positive charge. Now, once you assign positive charge to the top of the potassium, then coordination sphere will be respectively negative. So once this one is positive, this one will be what? Negative. So once you've assigned the correct charge on top of the two, the next thing you are now going to do is that you will need to balance the equation. You are going to check the compound again. How many potassium do we have? We have 3 potassium here. So this simply means that at the back of potassium here, I'm going to place 3. So any value you place at the back of potassium, you will also write it at the back of the what? At the top of the coordination sphere. So this is the correct ionization for this coordination compound. Now let us look at another example. Let us take this for an example. CONH3 Cl2. Now, if you look at this particular example here, we have CONH3Cl2. We may ask to ionize this particular compound. Whenever you want to ionize a particular compound, the first thing you have to check out is that does that compound has a counter-ion? Since it has a counter-ion, then you will write the counter-ion first. The counter-ion is what? Cl. Write it down. Cl. So once you've written the counter-ion, then you're going to write the coordination sphere plus CH sorry. Now, once you have written the counter-ion and the coordination sphere, The next thing we are going to do is to assign the correct charge. We all know that this is chlorine. It belongs to group 7, and whenever group 7 elements undergo ionization, they accept electron. So how many electrons do they accept? They accept only 1 electron. So this simply means that when chlorine undergo ionization, it becomes negatively charged. So that is why we are going to place minus at the top of Cl. So once you place minus at the top of Cl, then at the top of coordination square would be what? Positive. You will then check the question here, the compounds given to you. How many counter ion do we have? You have 2 counter ion. Then you are going to place 2 at the back of chlorine here. So once you place 2 at the back of chlorine here, any value you place at the back of the counter ion would also be written at the top of the what? Coordination sphere. So this is the correct ionization for this particular compound. Okay? Now, the next thing we have to do now is how to identify the types of coordination compound that we have and the type of ligands that we have. Now, before I move on to the types of coordination compound that we have to note something, that coordination compounds can also be referred to as complex compounds or simply complex or coordination entity. So you have to understand this very well, that the other name for coordination compounds can be what? Complex compound or simply complex, or you say coordination entity. Do not forget that in a particular coordination compound we have the central atom, which is also referred to as the coordination center, and we also have the ligand, which is also referred to as what? Complexing agent. So if they ask you that in a particular coordination compound, what is making the compound to be complex? That is simply the what? The ligand. Do you get that? Okay. Now let's also move on to types of coordination compound. Now, the type of coordination compounds we have, the first one is cationic compound. Let me put here complex. Cationic complex. Now, what are cationic complex? Cationic complex are the complex compound in which the charge on their coordination sphere is positive. For example, if we have this particular compound PtCl2 raised to power 2 plus. This particular complex is a coordination complex, and this particular compound is unionizable. It cannot be ionized. Who can tell me the reason why it cannot be ionized? Okay, because it doesn't have a counter ion. When a coordination compound does not have a counter ion, that coordination compound cannot be what? Ionized. So, but if you want to identify whether a particular coordination compound is cationic complex or anionic or neutral, the first thing you have to check is the charge on the coordination sphere. Right? If the charge on the coordination sphere is positive, then it is a what? Cationic compound. Do you get that? Or cationic complex. Okay, that is that. Now, let me give you another example. Let's say you have this particular compound CO NH3 Cl2. Look at this particular compound. They ask you that what type of compound complex is this? You are going to check that, okay, this complex compound, does it has a counter ion? Yes, it has a counter ion. So this simply means that if you want to know whether it is cationic, anionic, or neutral, you are to ionize the complex compound. You are to what? Ionize the complex compound. You will see that if we should ionize this complex compound, then we are going to get 2Cl minus plus CO NH3 2Cl plus 2. So since after the ionizing of this coordination complex, we got the coordination sphere to be positive, hence this coordination compound is a cationic compound. Okay, let's move on to the second one, which is anionic compound. Okay. Now, anionic. Now, a typical anionic compound is, we have something like FeCN6 all raised to power minus 4. Look at this. You will all see that the charge on this coordination sphere is negative, hence it is an anionic complex. Okay, what if we have K4, let's say we have K3 FeCN6. Now, if we should check this compound K3FeCN6, you are going to see that if we should ionize this coordination compound, then we are going to get 3K plus FeCN6. Now, since the charge on this coordination sphere, is negative, hence this is an anionic complex. Okay, now after we have also identified the anionic complex, let's talk about neutral complex. So whenever you hear neutral complex are the complex that do not have either positive or negative charge on it. So an example of neutral complex is this. Let's say you have something like neutral complex. For example, if we have NiCO4, you have this compound. If you check this compound, there is no counter-ion and there is also no charge on it. Hence, we can refer this compound to the word neutral. So neutral complex are the complex that has no positive or negative charge on them. And at the same time, there is no counter-ion, hence they cannot be what? Ionized. Those are the example of what? Neutral complex. Okay, we also have what we call homoleptic and heteroleptic complex. Okay, let's talk about homoleptic, heteroleptic. Now, whenever you hear homoleptic complex, these are complex that have similar type of ligand. And whenever you hear heteroleptic complex, these are complex that have different types of ligands. Now, if you check this compound, you see that in the square bracket, we have the central atom to be iron and we have the ligand to be what? Cn. And in this particular compound, if you check the coordination sphere, we have the central atom to be cobalt and the ligand to be NH3Cl. We're going to see that here we have 6 ligands. That is, we have 6 Cn. But all the 6 ligands we have, they are all the same. So whenever in a particular coordination compound, okay? Now, if you check the heteroleptic complex, we are going to see that the first ligand we have is Na3 and the other ligand we have is what? Cl. So this simply means that in this particular coordination compound, we have different types of ligand. Hence, it is referred to as what? Heteroleptic complex. Okay, that is that. Now, the last type of ligand we have can be referred to as mononuclear ligand, and what? Heteronuclear ligand. Sorry, we have mononuclear ligand. And we have polynuclear ligands. Now, once you hear mononuclear ligand consists of only one central atom. And once you hear polynuclear ligands, it consists of more than one central atom. So that's the difference. Those are the difference between mononuclear ligands and what? Polynuclear ligands. Now, the next thing we are now going to move on to now is the types of ligand. You know, sorry, here should be mononuclear complex. Mononuclear complex. Polynuclear complex. Correct that. So we are going to move on to types of ligands that we can have. You have to know something, that the types of ligand we can have can be subclassified into two. The types of ligand we can have can be subclassified into two. Now, let's talk about the classification of ligands in full now. Now, the classification of ligands can generally be done in two ways. The first way is the first type of ligand is classification based on charge. Or we can also have the classification based on density. Now, let's firstly talk about the classification based on charge. Now, if we are talking about the classification based on charge, we can have the number one, anionic ligands, those that are negatively charged, like FCl, etc. We can also have neutral ligand. These are the ones that are negatively charged, that are neutral. Examples are NH3, H2O, CO. And we can also have the cationic ligands. and an example is NO plus. So this is a classification of ligands based on the what? Charge. Anionic ligands, those are the ligands that are what? Negatively charged. Neutral ligands are the ligands that don't have any charge. And examples are what? NH3, H2O, CO. And the last one is cationic ligands. Examples are what? NO plus. So if you want more examples of anionic, neutral, and cationic ligand, please go to the Mfct Telegram channel. The name of the Telegram channel is Mfct Academy. So if you join the group, you are going to see more examples of anionic ligands, neutral ligands, and cationic ligands in the Telegram channel. Thank you. Now let us move on to the classification of ligands based on what? Denticity. Based on denticity. Someone will be like, are we talking about dentistry here? No. Whenever you hear denticity of a ligand, denticity of a ligand, notes. Of ligand simply means binding sites of the ligand. Of the ligand. So based on the binding sites of a ligand, ligands can be subclassified into two. The first one can be what? Non-chelating. Or we call it monodentates. Or unidentates. The next one is chelating ligand. This can be bidentates, can be tridentates, it can be ambidentates, it can be polydentates. Okay, so based on the denticity, that is based on the denticity, based on the denticity of the ligand, that is the density of the ligand simply means the binding site of the ligand, then ligands can be subclassified into non-chelating and what? Chelating ligand. Now, what is non-chelating ligand? Non-chelating ligand are the ligand that has only one binding site. Possess only one binding site. Examples are NH3, F, Cl-, etc. Also, go to the Telegram channel, Mfct Academy. You are going to see more examples of what? Monodentate or unidentate ligand. So, non-chelating ligand are the what? Monodentate or unidentate ligand. Whenever you hear mono or uni, it simply means what? One. So this simply means that when you hear monodentate, It simply means that it has what? One dentate. Denticity simply means the binding site. So it has one binding site. Mono or uni still means the same thing. You have what? One binding site. So example is what? Na3FCl minus. So they are the example of what? Monodentate ligand. That is to say they have only one binding site. So if you are not talking about the chelating ligand, if you are talking about the chelating ligands, these are the ligands that has more than one binding site. Possess more than one binding sites. Now, the chelating ligands are the ligands that possess more than one binding site. That is, they possess like 2 binding sites, 3 binding sites, 4 binding sites, 5 binding sites. So, if they possess 2 binding sites, we refer them to as what? Bidentates. If it is 3, we refer them to as what? Tridentates. If it is 4, we refer them to as what? Tetradentates. And if it is many, we can refer them to as what? Polydentates. Now, let me make some clarification here. If we are talking about bidentates, we can also refer it to as what? Didentates. Bidentates or dentates. Those are the ones that has what? 2 binding sites. 2 binding sites. They have 2 binding sites. An example of a common bidentate. Examples. Number 1, oxalate ion. You have to know something, that oxalate is coming from oxalic acid. So we are talking about oxalate ion. This is when we are talking about oxalic acid or ethane dioic acid with the general formula HCOO This is what? Ethane 1,2 dioic acid. It consists of what? 2 binding sites. This is one part, this is what? Another part. So an example of a bidentate is what? Oxalate ion. Another example is actually ethylene diamine. So ethylene diamine is another example of a what? Bidentate ligand. Now, for the ethylene diamine, the formula can be now for ethylene diamine, the first is what? NH2. The formula is Na2CH2CH2NH2. So the first binding site is what? NH2, while the second binding site is what? NH2. Do you get that? So that is an example of what? Ethylene diamine. You would remember that when I was talking about example of monodentate ligand, that was what? Amine, NH3. Do you get that? But for your bidentate, we have what? Ethylene diamine. One part is Na2, another part is what? Na2. So they have 2 binding sites, which can be used to bind to the central atom. You will now note something. What I want you to note now is that when the 2 binding sites are the same, as this example, we can refer to as what? Bidentates. But when these 2 binding sites, when they are different, then we are going to refer it to as what? Ambidentates. ambidentate. Ambidentate. Okay, let me show you something about that ambidentate. Ambidentate. A common example is SCN minus. Now, ambidentate ligand are the ligand from what? Bidentate. The major difference between ambidentate and bidentate is that in bidentate, the two binding sites are the same, but in ambidentate, the two binding sites are different. So, an example is SCN minus. This is the first binding site, and this is the what? Second binding site. And you are going to confirm that these two binding sites are what? Are different. Hence, it's an example of what? Ambidentate. Now, a common and a good example of polydentate. Polydentate. Or multidentate. A common example is ethylene ditetracetic ion. The full name is what? Ethylene ethylene ditetracetic ion. So that is a common example of what? Polydentate ligand. And for this polydentate ligand, it can also be referred to as what? Multidentate, or you simply refer it as what? Polydentate. So they consist of what? Many binding sites. So in this ADTA4 minus, we have what? 4 binding sites. So that is the types of ligand based on what? Denticity. Now guys, let's quickly move on to oxidation number and what? Coordination number. Oxidation number. And coordination number. Now, in a simple way, whenever you are talking about coordination number, it simply means the number of ligands that are binding to the central atom. For example, let's say we have K3 FeCN6. We all know that K is potassium and it is a what? Counter ion. The central atom and the ligand are found only in the square brackets. This simply means that Fe is the central atom, while the ligand is what? Cn. So how many Cn are we having here? That is what? 6 Cn. So this simply means that the coordination number, let me write something here, of central atom. This simply means that the coordination number of central atom Fe is 6. So the coordination number is very simple. It is just the number of the ligands binding to the what? Central atom. So the coordination number is what? Is 6. Okay, what if you want to do the oxidation number? And not something. We majorly talk about the coordination number of the what? Central atom. Or I say the coordination number of the coordination center. If you follow the class from the beginning, I said that the central atom can also be referred to as what? Coordination center. So the question can come as what's the coordination number or the coordination center, coordination number of the central atom or the coordination number of the coordination center. So the answer is what? 6, the number of ligands that is here. But if you want to calculate the oxidation number of the central atom, you have to follow the same rules. You have to follow the same rule. The same rule as the rules guiding your oxidation number in inorganic chemistry that you did in 4th semester. Now, you all know that whenever you want to look for the oxidation number of a particular element, you have to add all the elements, you have to add the oxidation number of all the elements together and equate it to the charge the compound carries. They get that? The only addition to the oxidation number of the coordination compound, the only addition is that you are to represent the oxidation number of a neutral ligand as 0. The only difference or the only addition to the oxidation number of coordination compound is that the oxidation number of neutral ligand should always be what? 0. And this simply means that you must know the examples of the what? Of the neutral ligands of So let me give you a few examples of neutral ligand. We can have what? H2O. And the ligand name is what? Aqua. We can have CO. And the ligand name is what? Carbonyl. We can also have NH3. And the ligand name is what? Amine. And we can also have ethylene diamine. So the examples of the neutral ligand, let me write it in. Examples of neutral ligands. Number 1 is H2O. The ligand name is aqua. Number 2 is NH3. The ligand name is amine. And note, please, the amine, the ligand name of this NH3, which is amine, is what? Double N. We also have CO. The ligand name is carbonyl. And we can also have ethylene diamine. This is ethylene diamine. You already know this is a lot of what? Bidentate ligand. Ethylene diamine, EN. These are the example of what? Neutral ligand. So whenever you see a neutral ligand in a coordination compound, their oxidation number would be what? 0. But let me do the coordination the oxidation number of the central atom here. So for K3 FeCN6, if you want to do the oxidation number, you will just say how many K do we have here? That is 3. That will be 3K plus Fe plus 6Cn to equal 0, because the total charge there is what? 0. So this is K, that is potassium, it belongs to group 1, and the oxidation number of group 1 is what? Plus 1. So this one will now be 3 plus 1 plus Fe plus 6, and this will be what? Minus 1 equals 0. The oxidation number of Cn, you have to know that Cn stands for cyano, and it is coming from cyanide, which is what? Cn minus. The oxidation number of Cn is what? Minus 1. Please notice very well. The oxidation of Cn is minus 1. So this one will now give us 3 plus Fe minus 6 equals 0. Now what is 3 minus 6? That is minus 3. Then this will be Fe minus 3 equals 0. If this minus 3 goes to the other side, then that will be what? Fe equals plus 3. So this simply means that the oxidation number of Fe in this coordination compound is what? Plus 3. Okay, let's look at an example, another example. Let's look at another example. Now, let's look at this particular compound CONH3 Cl2. So for this particular, if you want to know the coordination number, the coordination number would just be the number of ligands that are present in the square bracket. Now, the first ligand here is Na3, the second ligand here is what? Cl. So this simply means that we have 4 ligands present in the square bracket. So, sorry, we have 2 ligands, because Na3 is one ligand, Cl is another ligand. So we only have 2 ligands present in the square bracket. Hence the coordination number is what? 2. Okay? Now, if you want to do the oxidation number, if you want to do the oxidation number, let's do it. So this will be CO plus NH3 plus Cl plus Cl2 to equal 0. Remember that you are to treat the neutral ligand as a single entity. So that is why you have to write Na3 here. So that is how to do it for coordination compounds. So the next thing you have to note is that the oxidation number, this Na3 is an example of a what? Of a neutral ligand. So the oxidation number of Na3 would be what? 0. Why this Cl? Yeah, I can write 2Cl. Why this Cl? The oxidation number of Cl would be what? -1, because it belongs to group 7 elements. So this will now be CO plus 0. The oxidation of Na3 is 0 plus -1 plus 2 minus 1. That's equals to 0. And if you check this, this is -2, sorry, -1 minus 2. -1 minus 2 will give us what? -3. So this will now turn to 0 minus 3 equals 0. So the oxidation number of CO would be what? Plus 3. So the oxidation number of CO would be plus 3. So that is how to do it. So you have to treat the what? The neutral ligand, the oxidation number of the neutral ligand as what? As 0. Okay, that is that. So the last thing we have to do for today is how to name a coordination compound. The naming of coordination compounds. But you have to know something, that the naming of coordination compounds always come with some rules. So let me write out the rules that is guiding the naming of coordination compounds before we apply it in what? In solving of some question. Okay? Rules of naming coordination compounds. Number 1, name for a ionic compound. name cationic entity before anionic. The rule number 2, name ligands before central atom. The rule number 3, name ligands alphabetically. Okay, and the rule number 4, in naming of central metal atom, if the complex is cationic or neutral, metal name is unchanged, but if it is anionic, metal name ends in ATE. Number 5, write the oxidation number of the central atom immediately after the metal name inside parentheses. Okay, so these are actually the rules. These are actually the rules that are guiding the naming of a coordination compound. Now guys, let us say we are to name this complex. We want to name K3FE CN6. So let's say you want to name this compound K3FeCN6. The first thing you have to notice is that the rule number 1 is that for ionic compound, that is for the compound that can be ionized, name cationic entity before anionic entity. So this simply means that we are to ionize this compound. So the ionize will give us 3K plus FeCN6. So the first thing is that we are to ionize the complex. So the ionizing of this complex actually gives us what? 3K plus FeCN6 3 minus. So you already know how to ionize. We've done that earlier. So this simply means that the cationic entity is what? Is the counter ion. Hence, name the counter ion first. So after you have named the counter ion, then we are now going to name the coordination sphere. So if you want to name this coordination sphere, we are going to follow the number 2. The rule number 2 states that name ligands before the central atom. Are you there? And you know that the ligand here is what? Cn. How many Cn do we have? We have 6. Now, if we have 2 ligands, we will call it, we are going to use bi for it. Now, let me be more specific. If we have 2 monodentate ligand, we will use bi. If it is 3 monodentate, we are going to use tri. If it is 4 monodentate, we are going to use tetra. If it is 5 monodentate, we are going to use penta. If it is 6 monodentate, we are going to use hexa. If it is 7 monodentate, we are going to use what? Hepta. But if it is bidentate or tridentate or polydentate ligand, are you there? So we are going to use bis for 2. We are going to use bis for 2 bidentates. We will use tris for 3 bidentates. We will use tetrakis for 4, and we use pentakis for 5. So that is for if we have like 2, 3 or 4 bidentates, tridentates or polydentates ligand in that compound. Do you get that? So, but here Cn is an example of a monodentate ligand, hence we are going to use what? Hexa for 6. So ligand name is hexacyano. You have to know that this Cn represents, the ligand name for Cn is cyano. The ligand name for Cn is cyano. So that is that. The next thing we are now going to do is that after we have named the ligand, name central atom. We are going to see that the central atom we have here is what? Fe. The central atom we have here is Fe. So this Fe represents ion. Are you there? So you will now follow the rule number 4, that in naming of a central metal atom, if the complex is cationic or neutral, metal name is unchanged. The metal name is unchanged. But if it is anionic, if the complex is anionic complex, the metal name ends in ATE. So everybody, let us look at this particular complex. Is it anionic, cationic, or neutral? Okay, if you remember that from the beginning of this class, I explained how you can identify neutral complex, anionic complex, cationic complex. So in order to identify a neutral, cationic, anionic complex, it is by the charge on the coordination sphere. The charge on the coordination sphere is what? Negative. So this simply means that this particular complex is an example of anionic complex. Hence, since the complex is anionic, the metal name will end in what? ATE. If the central atom metal we have, if it is iron, the name will end in ferrite. If it is copper, the name will end in cuprate. If it is manganese, the name will end in manganate. If it is zinc, the name will end in zincate. If it is cobalt, the name will end in what? Cobaltate. Do you get that? It's by the rule number 4. So since the central atom, since the complex is anionic, the metal name ends in ATE, that is to say ferrite. Then we will calculate the oxidation number. The last thing is that write the oxidation number of the central atom immediately after the metal name. So everybody, we already know how to calculate the oxidation number of a central atom. Then this simply means that if you want to calculate the oxidation number of this, then oxidation number of Fe is plus 3. So since we all know that the oxidation number of Fe is plus 3, after we have calculated the oxidation number of Fe, then this simply means that we are done with everything we have to do. Hence, the name of the complex K3 FeCN6 would be potassium hexacyanoferrite 3. That's the correct naming of that particular compound. Okay, so once we've known this, now let me give you an example and you guys should drop the correct naming of the compound in the comment section. Yeah, but try this. K for FeCN6. Drop the answer in the comment section. The first answer I see will be compensated. So the last example I will do to call it a night is naming of CO3 NH3 5Cl. Drop the answer of this classwork in the comment section and let us name this. Now, everybody, do not forget, whenever you have a coordination compound that you want to name, the first thing you have to do is to check if the compound can be ionized. If the compound can be ionized, then you are going to ionize the compound and you are going to name the cationic entity before the anionic entity. You will now see that if we should ionize this particular compound, then we are going to get CO, NH3 5 plus Cl ions. So do not forget that we have talked about how to ionize a coordination compound before. So that was why we moved on directly to this. Now, after that, we now go for rule number 1, which states that for a ionic compound, name cationic entity before anionic entity. So in this case, we are going to see that the coordination sphere is the cationic entity, while the counter-ion is the anionic entity. So this simply means that we are going to name the coordination sphere before we name the what? Counter-ion. So in the naming of the coordination sphere, we are to name the ligands before the central atom. Okay, now if we want to name the ligands, we have to name the ligands alphabetically. Now, if you want to name the ligands alphabetically, you must be well acquainted with the ligand name of this compound. The first ligand we have is CO, which is the ligand name for CO is carbonyl. Also, the ligand name of NH3 is amine. Are you there? So alphabetically, amine comes first before carbonyl. So this simply means that we have to name amine before we name carbonyl. Now, how many amine do we have here? We have 5 amine. How many carbonyl do we have here? We have 3 carbonyl. Then the ligand name would be pentamine, tricarbonyl. So once we've named the ligand, then we are going to name the what? We are going to name the central atom. The central atom here is actually what? Cobalt. So you will now go to group number 4, you will check if in the naming of the central atom, if the complex is cationic or neutral, metal name is unchanged. You are going to see that this particular coordination compound is a cationic compound because the charge on the coordination sphere is positive. Hence, the name of the central atom cobalt would be what? Unchanged. And the central atom name would just be cobalt. So it will only change to cobaltate if the charge on the coordination sphere is negative. That is, if the compound is anionic. So after we have named the central atom, we are going to calculate the oxidation number. Okay, if you want to calculate the oxidation number of the central atom, I have taught you how to calculate that. So you just have to know that this carbonyl, this ligand carbonyl, and this ligand amine, they are both neutral ligand. So their oxidation number would be 0. This one will also be 0. So the oxidation number of Cl will be -1. So this simply means that the oxidation number of the central atom cobalt would be what? +1. Hence, the name of the coordination compound is pentaamine tricarbonyl. Pentaamine tricarbonyl cobalt 1 chloride. Cobalt 1 chloride. So this is where we are going to stop tonight. So if your name is Awal Adekunle, please text me on WhatsApp for your tonight's giveaway. So thank you very much. We are going to continue tomorrow.